So here's a little review of the practice test that we worked on in class on Friday. We went through the first part of these in class, but I'll review it in case you missed something while we were talking about it. So the first question asks about the most uneven sharing. So uneven means that the two atoms are not sharing electrons equally. So that would be based on electronegativity difference. Remember electronegativity. Electronegativity increased as we went up and to the right on the periodic table, with the most electronegative elements being up here and the least electronegative over here. If you look at these elements, we have oxygen to oxygen, so their electronegativity would be the same, so they would be attracting electrons evenly. What you're looking for is the two elements that are furthest apart on the periodic table, so their electronegativity difference would be the greatest. And so in this case, that looks like it'd be H and O, because H is over here on the table and O is over here on the table. Number two, which of the following energy changes is the most exothermic, which means energy out? So this goes back to the Born-Haber cycle that we began this unit with, but there's a little video on the website from MIT if you'd like to watch that again, describing the process of the Born-Haber cycle. It's on the homework section, and it says the video from MIT. So the first listed here is ionization energy, and that's the energy to remove an electron. So ionization energy deals with removing an electron. The second, electron affinity, deals with adding an electron. Lattice energy means for the ions to attract, or ions coming together, attracting each other. And bond energy is the energy required to break a bond. Well, when we talked about the Born-Haber cycle, we know that ionization energy was always required, so energy in for that. To break a bond, energy is required, so energy would go in. Electron affinity and lattice energy both release energy usually. Lattice energy always releases energy, and electron affinity releases it most of the time. But the most exothermic part of the Born-Haber cycle was lattice energy. I showed you a picture. You can find that picture on the website also back with the MIT lecture, but there's a picture showing lattice energy compared to the other energies, and lattice energy was by far the largest energy change when you form an ionic bond. Okay, insoluble will be the ones that stick together the best. So you look at the charges, +1 and -1, or the charges on potassium and chlorine. Magnesium and chlorine would be +2, -1. And once again, these charges are based on valence electrons, or are called oxidation states. The magnesium would lose 2 electrons, that's why it's got a +2 charge. Since it has 2 valence electrons, it'll lose 2 electrons. Chlorine has 7 valence electrons, so it's going to gain 1 more. So that's where it gets the -1 charge. Sodium's +1, fluorine's -1. Same kind of logic on all these. You go by the valence electrons. +2, -2. Oxygen has 6 valence electrons, so it has room for 2 more. That's why it's a -2 charge. And potassium is +1, -2. You have to pardon the middle schoolers over there. So the potassium here, 1 and 2, 1 valence electrons, 2 and 6 valence electrons for sulfur. So the ones that stick together the most would be most likely to be insoluble, and the ones that would stick together the most would be the ones with the highest charges. So you're looking at 2 and 2, and that's why the magnesium oxide was the answer to that. Now the easiest to pull apart would be based on charge again, but also size. So let's talk about charge first. That's +1, -1. +2, -1. +1, -1. +3, -3. +1, -2. So the ones that stick together the most would be this one, but we want the ones that are easiest to pull apart, so we're going to go to the lower charges. So we're looking here or here. Now this is where I use the analogy of the ping pong balls in a trash can. So if you have a trash can full of ping pong balls, as opposed to a trash can full of soccer balls, you can see that there'll be more space in this one, more open space, And the ping pong balls, since they're smaller, will be able to get closer together. Well, given equal charges, the ones that are closer together will stick together better. Like the magnet illustration that I showed you in class, when the magnets get closer, they attract each other more. Well, the smaller of these atoms is the Na compared to the potassium, and the fluorine compared to the chlorine. And you know that based on your periodic table trends, that atoms get bigger as you move down the columns. Since NaF is smaller than KCl, it will stick to, these two ions will stick together better, and KCl will be the easiest to separate. And so when I say it's the easiest to separate, that will mean it has the lowest melting point and the lowest boiling point. All right, number 5, we know that the steps that involve a loss of energy, we talked about earlier. Heat of sublimation, we didn't talk about that one. Lattice energy, we talked about out. And ionization energy, we said had to be in. Bond energy had to be in. We did, when you're talking about sublimation, subliming means they go from solid to gas. So would it take energy to make something go from solid to gas? And the answer to that would be yes. So that would be energy in as well. So our answer is lattice energy. Okay, which one would lose 2 electrons? There were 2 answers on this one. It's based on valence electrons. So I'm going to write down the valence electrons for all of these. 2, 2, 3, 1, 1. So the ones that would lose 2 electrons are both calcium and magnesium. Okay, this one, we had the nitrogen and the magnesium atoms making magnesium nitride. The nitrogen atoms have this valence electron arrangement, 1, 2, 3, 4, 5. Now, if you have 2 of them, there would be 3 open spots in both of them because they would like to have 8. So you could put another one here, another one here, another one here. So 2 atoms would gain a total of 6 valence electrons. So if magnesium has 2 to give away, there's 2. How many of these atoms would it take to give away 6? Well, you'd need 3 atoms. Each atom having 2 electrons. So that would make the 6 that are needed to fill up the nitrogen. So the answer was 3, which is not polar. For these kind of questions, you will probably need to start thinking about drawing dot diagrams, but for this one you can tell quickly which is not polar because you know that hydrogen bonded to hydrogen would have a completely even attraction for electrons. So since they have even attraction, they are absolutely not polar. All right, now this question wants to know which one has the strongest intramolecular bond. Intra means inside the molecule. So when you draw the dot diagrams, I'm going to draw them quickly because I know what they are. You have to know how to draw these dot diagrams. And we've gone through these a lot in class, so it should be no problem to come up with this structure. The nitrogen dot diagram would look like this. The water dot diagram looks like this. And the HCl dot diagram looks like this. Remember that hydrogen only gets 2 electrons. So which is the strongest of these bonds? The double bond here, the triple bond here, single bond or single bond? Well, the triple bond would be the strongest attraction between the 2 atoms because they're sharing 3 pairs of electrons, a pretty strong bond. I'm going to do number 10. I'm going to find a different location, it might be a little quieter. So a process releases more energy than is put in. So you put some energy in, but you get more energy out. Is that endothermic or exothermic? So that would be exothermic. All right, I'll stop there, and we'll do the rest on separate videos.